Good morning, students. We are discussing the unit 4, that is the chapter chemical kinetics. Already we have discussed rate law or rate expression, which is a differential rate equation, but this is not always convenient to determine the instantaneous rate. So to avoid this difficulty, we can integrate the differential rate equation to have a direct relation between concentration of reactants at different times and rate constant. And we will study here the integrated rate equation only for zero order reaction and first order reaction. Today we will see the integrated equation for zero order reaction. So today's topic is integrated rate equation for zero order reaction. So consider a zero order reaction. So consider a zero order reaction. R gives P, reactant gives product. So for this zero order reaction, the rate is expressed as rate that will be equal to minus dr dt, which will be equal to K concentration of R to the power 0. So here the power to the concentration of the reactant, that will be equal to 0 because this is a zero order reaction, or minus dr dt, that will be equal to K, R to the power 0 equal to 1. So this is equal to K. Or if you rearrange this, then dr, that will be equal to minus K dt. Now if we do the integration in both sides, so integrating both sides, what we'll get? So integration of dr, that will be equal to integration of minus K dt. Now we have to know here the integration. So those which do not have the mathematics, you simply remember that integration of dx, that is equal to x. So we will apply this here. So integration of dx is equal to x. That means therefore integration of dr, that will be equal to r, which will be equal to integration of minus K dt. K is a constant, so it will come out. So minus K integration of dt, that is equal to t, and there will be one constant of integration. So whenever we do the integration, then that constant is coming automatically, so that you just remember. So here where I is the constant of integration, I is the constant of integration, and now this is the equation 1. So now whenever t is equal to 0, that means just at the starting of the reaction or just before the reaction, means time is equal to 0, then concentration of the reactant, that will be the initial concentration of the reactant. That means when t is equal to 0, time 0, that means at the starting of the reaction or just before the reaction. Then concentration of the reactant, that will be the initial concentration. So that means R, that will be equal to R naught. Now if you substitute the value in this equation, so substituting the values in equation 1. So when t is equal to 0, R will be equal to R naught. That means R naught, that will be equal to minus k into 0 plus I. That means, that is, I will be equal to R naught. Now again, if you put the value of I in the equation 1, that means if you substitute the value of I in the equation 1, then what we will get? So again, substituting the value of I in equation 1, that implies I is equal to R naught. So if you put this value here, R will be equal to minus KT plus R naught. Now you see here, this is an equation of straight line. That means y is equal to mx plus c. If you plot concentration of reactant versus time, that means R versus T, if we plot, then we will get a straight line, because it is an equation of straight line like y is equal to mx plus c. So now we will plot R versus T and we will get a straight line with negative slope minus k, with intercept R naught. So that we will see here now. So if you plot concentration of reactant against time, that is R against T, we get a straight line with slope minus k and intercept R naught, means initial concentration. So you see that plot, that along the y-axis we will take concentration and along the x-axis we will take time, means R versus time. So then we get a straight line with slope negative, that with negative slope. So initially at time 0, the concentration of the reactant, that is the initial concentration, that is R naught. This is the initial concentration, that is your R naught. R naught. So it will go in this way. It will give a straight line with negative slope. That means slope equal to minus k, and this is the intercept. So intercept, that is equal to R naught. So this is the variation in concentration versus time, concentration of reactant versus time for zero order reaction. So where slope is equal to minus k and intercept is initial concentration R naught. Again, that straight line equation r that is equal to minus kt plus r naught. So if you rearrange it, then we'll get, or k will be equal to kt, you bring it this side, so k that will be equal to r naught minus r divided by t. So this is the integrated rate equation for the zero order reaction that we have to remember. So we have to remember this, and accordingly we have to do some numericals that we will do next. So we'll see one example of a zero order reaction. So example of a zero order reaction. So one example, that is decomposition of ammonia gas in the surface of hot platinum catalyst to give back nitrogen and hydrogen gas. Hydrogen gas. So here this one example of a zero order reaction. So this is the integrated rate equation for the zero order reaction. So in the next class we will see the integrated rate equation for the first order reaction. So this is for today. Thank you.